Hello everyone, welcome to another video of the introductory course on drive and control of three-phase induction motors. Here in this video we will start a new part, that is the per phase model of three-phase induction motors. The aim is to review the derivation of the per-phase equivalence circuit model of three-phase induction motors. As you know, we can use the per-phase equivalence circuit model of the motor to evaluate the steady-state performance. Yes, we can calculate characteristic curves such as the torque speed curve, the variation of the stator phase current versus the slip, or rotor phase current versus the slip, and so on. Here the focus is on a steady state performance, and in the next part, when we discuss the two-axis model of the motor, we can evaluate the dynamic performance of the motor. Anyway, so let's start the derivation of the per phase model of the motor. Before that, let's review the structure of induction motor, the rotor types, and few concepts. Yes, just for review, here in this image, you can see a structure of a typical induction motor, mechanical parts. This image is from this great reference. Yes, this is a very good reference. I recommend to prepare this reference and read it carefully. So here we have the stator iron core. Yes, and this is the stator winding. In this case, we have a copper winding, and in the case of three-phase induction motors, we have a balanced three-phase winding. All phases are identical. Yes, just we have a shift between the magnetic axis of the phases. Yes, we are going to generate a rotating field, a sinusoidally rotating field using the stator winding. This is the rotor core. Yes, you can see the laminations of the rotor core, and here we have the end ring. In this case, we have a cage rotor. Yes, with this is the aluminum cage, and here we have the end rings. These are rotor cooling fans that are considered at the end of these end rings to circulate the air inside the frame for better cooling of the rotor core, to remove the generated heat from the rotor, yes, to the stator, and so on to the ambient. Here we have the front bearing, and this is the rear bearing. The load is attached to the shaft from this side. Here we have this fan attached to the shaft at the rear side of the motor to circulate the air, to drag the air from here and fluid over the external fins that are on this green frame. And here we have the terminal box. So you can check these parts for your benchmark induction motor that you prepared to follow this course. Yes, in the previous video we discussed the benchmark motor that I want to use to do experiments and tests. And if you have access to lab, or if you prepared a low power induction motor, you can check these parts. Anyway, so for induction motors, as you know, we have two rotor types: a squirrel cage rotor and a wound rotor. In the case of the squirrel cage rotor, we have a laminated rotor core, and the cage of the rotor is manufactured using die cast technology. Here we have end rings, and these are rotor conductor bars that are skewed to reduce the noise, the torque ripple. You know these concepts. And also we discussed the electromagnetic design of induction motors in one of courses that is available in the channel. So here we have the wound rotor induction motor. When we want to have access to windings to fed them, or if you want to use external resistances to modify the torque speed curve to increase the starting torque, in these applications we use the wound rotor induction motors. Here in this case we have three identical phases on rotor core that are connected in a star way, and these terminals are connected to the external resistance or power supply using these slip rings and brushes. Okay, so this type of rotor is used for specific applications. Here in this image, we have the cross section of the active parts. Here we have the rotor lamination, the stator lamination, the stator winding objects, and the rotor cage. Here I did a finite element simulation to calculate the field that is generated by the stator winding. I did this simulation using EMDLab, and the source code of this simulation is available on GitHub. You can download it and run it in MATLAB to visualize this image. So this is the 2D cross section of the benchmark induction motor that I have. The number of stator slots is 36. The number of poles is 4, and the number of rotor bars is 26. So this 4-pole magnetic field is generated using this three-phase winding. Here we have the phase A, the phase B, and the phase C. Yes, we have a 4-pole induction motor. Here is the first zone of the phase A. As you know, we have a single layer winding for this benchmark motor, and the number of stator slots is 36. NS is equal to 36. So what is the number of slots per pole per phase? Is 36 divided by 4 poles times 3 phases. This is equal to 3. So the number of coil arms per pole per phase is 3. For these 3 coil arms, the direction of the current is into the paper. When the color of the coil arm is red, it means that the direction of the current is into the paper, and for these coil arms, the direction of the current is out of the paper. So here we have the magnetic axis of the phase A. Yes. And where is the magnetic axis for the phase B? Here, this is into the paper, out of the paper. And here we have magnetic axis of the phase B. For the phase C, this is out of the paper, into the paper. And when we have these currents into the paper, out of the paper, we have this magnetic field. These arrows show the direction of the field. Yes, so we select this one, considering the first peaks that we have in the radial component of the magnetic field. Consider this image. Yes, here we have the magnetic axis of the phase A. We discussed these concepts in the induction motor design course. So yes, this is the magnetic axis of the phase C, and when we excite 3 phases of the motor, the stator winding, using balanced 3-phase currents, we have a rotating field. Later we will generate the rotating field, and we will write a MATLAB code for it. So, what is the aim? The aim is to propose an abstract model for the motor to use it for the drive purposes. Yes, for development of the control algorithms. So here in the finite element model, as you can see, we have detailed field solution. We can consider all nonlinearity effects, iron losses, the effect of slottings, and the effect of higher harmonics that we have in torque ripple, and so on. But the aim is to simplify and have an abstract model, yes, to develop the control algorithms using that. But how we can develop the abstract model? Here we have a stator and rotor laminations in the abstract model. Yes, this is the rotor lamination and this is the stator lamination. We have a uniform air gap here in this figure. I neglected the effect of slots. Okay, so here this model, I am discussing this abstract model for a two-pole motor. Easily we can extend it for motors with a higher number of poles. So here we have the phase A. These two currents show actually the phase zones. Yes, here we have one phase zone and this is one phase zone. We can have a number of slots here and we can distribute the phase zone, this phase zone of the phase A here into a number of slots. But I use this notation that is common in right drive textbooks, yes, to show the phase A. Here the direction of the current is out of the paper and here is into the paper. So this is the phase A of the stator winding, and if we excite the phase A, we will have this kind of field solutions. Here in this case I only considered one coil. Okay, in this field solution we have the full model, and when we excite these coil arms for the phase A, we have this field solution. But what if we only have one slot and excite it? Yes, for this coil arm, the direction of the current, if I consider it out of the paper, similar to this one, and for this one into the paper, we will have this field here that is in this direction. So here is the direction of the flux density flux density lines and the flux density vectors that we have. So here in this figure you can see the flux density magnitude, and here when the cross section of flux lines is lower, we have a higher flux density amplitude. Yes, because you know that the all flux that is crossing this part of the model, this part of the model, let me use this color, this part of the model, this flux is the same as this flux. Okay, so here we have lower cross section and consequently we have a higher flux density magnitude. So when we have this field solution, we can plot flux density vectors, B vectors, in the middle of the air gap. Yes. So here we have both flux lines and B vectors in the middle of the air gap, and in this figure just I showed the B vectors in the middle of the air gap. Yes, here for this side the direction of the field is inward, radially inward, and here we have radially outward field. So the important curve that we have is the flux density waveform. What is the flux density waveform? If I use the cylindrical coordinate system, I can draw two plots considering the field solution flux density vectors that we have in the middle of the air gap. If you consider this x-axis and this as the y, so if I consider, for example, this point, let's consider this point, we have this flux density vector. So let me use an exaggerated amplitude for it. So this is b. Now let's focus on this part in the cylindrical coordinate system. If you consider this as the outer surface of the rotor core, and this is inner surface of the stator, and this is the middle of the air gap. So we have this b component, b, and we have this x and y coordinate system, and this if you draw a line here, yes, from the origin to this point and extend it, we can decompose this b vector into two components: the radial component br and the tangential component. So let me use another color here. Okay, so this is the radial component br, and this is bt, tangential component. So I considered this point. I can plot this graph. This is theta, the circumferential coordinate in the cylindrical coordinate system. This is theta. Okay, and the y-axis can be br or bt. So here we use br, the radial component. So yes, if we plot br versus theta for this example, we have something like this. Here when theta is 0, we have peak value for the br, for example 0.8 Tesla. Here we have this br, and when theta is equal to pi divided by 2, pi, 3 pi divided by 2, and 2 times pi. So here we have this reduction. We have this value for the br. For this side, the direction of the flux density vectors is inward actually, and here we have this br again. So yes, this is the flux density waveform. You can plot the tangential component also. Why this flux density waveform is important? Because the aim from distribution of the current for this phase zone into a number of slots is to have a sinusoidal flux density waveform in air gap. Here in this case, only I have one coil, and consequently we will have a rectangular waveform that is not good. As you know, for this waveform we have high amplitudes for higher harmonics, yes, but you know that the fundamental harmonic is important for us to generate a good average torque. So now let's visualize the flux density waveform for the benchmark motor. When you run the finite element simulation using EMD-Lab, simply you can export the field solution that we have in the middle of the air gap. Here we have a 4-pole induction motor, and you can see a zoom in view here. So clearly you can realize the effect of slot openings, yes, and variations that we have for the radial component and tangential component of flux density vectors in air gap. So here you can see the flux density vectors also inside the rotor and stator laminations. Okay. Here I generated these two graphs using the EMD lab. This is the radial component BR, and here we have the tangential component BT. Clearly, you can see the effect of slot openings. But what is important is the fundamental harmonic of this waveform. Yes, so we can write a Fourier series for this waveform BR as a function of theta. That is the summation of the peak values times the cosine of, right, I times theta and so on. So you know that. What is important for us is the fundamental harmonic. So if we neglect all higher harmonics, in this case, I can write BR, the peak value of the fundamental harmonic times cosine of 2 times theta, because we have a 4-pole induction motor. So this is not equal. Actually, I should write approximation in the abstract model. Okay. Yes, we can develop a detailed model for the induction motor, consider all higher harmonics, yes, that these models are available. But the aim here was to explain the concept of the flux density waveform and this approximation that we have. So, yes, now let's discuss the concept of the magnetic axis. Here, clearly, you can realize that the peak value of the field that is generated is in this direction. Yes, we generated this plot. This is theta, and this is BR. So this is pi divided by 2 pi, negative pi divided by 2, negative pi. For a single coil problem, we have this flux density distribution. But for a sinusoidally distributed winding, for an ideal case, we have this fundamental harmonic. Okay, so here is the magnetic axis that we have peak value here. This is the magnetic axis of the phase A. Graphically, you can show it here, right? This is a space vector. So this is important because we use it later when we develop the abstract model. So suppose that we have an ideal winding that can generate a sinusoidally distributed radial component of the flux density in the air gap, this ideal case. Yes. So for this case, we have again the magnetic axis here, and we are going to derive the abstract model considering the fundamental harmonic of the waveforms generated by the phases. So here is the magnetic axis of the phase A. And when we have the phase B with 120 degrees phase shift for a two-pole motor, when the number of poles is 2, mechanical degree, yes, is equal to electrical degree. So Here we have 120 degrees mechanical phase shift and also electrical phase shift. This is the first zone of the phase B, and this is the second zone of the phase B. And here we have the magnetic axis of the phase B, that is in this direction. And finally, we have this magnetic axis for the phase C, and you can see the direction of the currents in these phase zones. Okay, so let's review. Here we have the abstract model, the laminations, rotor and stator laminations, uniform air gap. We assume these two zones for the phase A. We reviewed this single coil problem to derive the flux density waveform distribution in air gap. We tried the same simulation for a 4-pole induction motor and derived these curves. The fundamental harmonic is important. Considering the concept of the peak value, we defined the magnetic axis, and then we considered the fundamental harmonic to have actually this abstract model and continue the derivation of the equivalence circuit of the three-phase induction motors using this abstract model. So this is the phase B, and finally we have the phase C. So how the rotating field is generated by the stator winding. When we have a balanced three-phase winding, we should have a rotating field in air gap. So let's write a MATLAB code and visualize this important concept. Okay, so now I am going to write a MATLAB code to visualize the rotating field generated by the stator winding. So here, let's write this code, clear the command window, close all available figures, and clear the defined variables. This is the initialization of the code, initialization of the code. So I am going to plot also the stator and rotor laminations to have a good visualization. Here, let's define T as a circumferential coordinate system from 0 to 2 times pi. Consider 100 points and plot the rotor and stator laminations. Let's consider these dimensions. This is the shaft. This is the outer surface of the rotor, the inner surface of the stator, and this is the outer surface of the stator. So here I am going to consider this as the R1, and the radius from the center, yes, the origin up to the middle of the air gap, let's call this R2, and this radius R3. Also we have the air gap thickness. So let's define these variables. R1 equal to 2, for example, R2 equal to 4, and R3 equal to 6. The air gap thickness equal to 0.4. Yes. So here we have the inputs or dimensions. And this is the circumferential coordinate T, but yes, here I am going to use it to plot these circles. So this is just a geometrical variable. So we can use the plot function to plot the outer surface of the stator R3 times cosine of t and R3 times sine of t. So if I run this code, as you can see, we have this circle, but I am going to draw circles that are filled with this color, for example, for the stator and rotor lamination. So I can use the fill function and specify a color here. You can specify RGB, so 0.6, this color is good for the lamination. So this is the stator, and we can use this command axis of equal to visualize it better. Now let's add this one. What is the radius of the air gap? Is R2. The radius of the air gap is R2, is the parameter that we considered, and this is the gap. So here I can use the fill function. Instead of R3, I can write R2 minus gap divided by 2 plus, So here, and let's use the white color here. So we can generate this graph. Here we should write figure, hold all plots. This is the stator lamination. For the rotor lamination, we can use the same method. Here we have R2 minus gap divided by 2, and here we have R1. That is for the shaft. Okay, so here we have this geometry. You can now modify these parameters to visualize these laminations better. So this visualization is good. You can change the air gap thickness also. What is the field generated by the phase A? So here in this case, if we consider this as the x-axis and this as the y-axis, this is x and this is y. We have this phase zone. The direction of the current is out of the paper, and here is into the paper. This is the field generated by the phase A for a two-pole motor. In ideal case, you can write this function b, that is a function of theta, is equal to a peak value. This is b1 peak value, the fundamental harmonic, times cosine of theta. Yes, this is the radial component. Suppose only we have the radial component and now neglect the tangential one. I want to visualize this field in the middle of the air gap for the phase A. So here I can use the quiver function. So I need to generate points first in the middle of the air gap. I can write this x equal to R2 times cosine of t and y equal to R2 times sine of t. So I want to use the quiver function to plot this vector field x, y, and we need to specify x and y components of the field. Yes, the vector field. When you have a vector field in MATLAB and you want to plot it, a vector field like this, f, you should specify x, y coordinates of the point and the fx and fy components of the field vector that is attached to this point. So in this case, if we consider this point, this is the BR. If we only consider the BR and neglect the tangential component, but in real case, we cannot neglect the tangential component. If you are familiar with the Maxwell stress tensor, the tangential component generates torque. Okay, so it's important the tangential component and the radial component together generate torque. So yes, here I am going to visualize, and you can use this kind of visualizations later for your projects, for the control methods that you develop, that is really good. So if you consider this BR component, and I want to decompose it into BRX and BRY. Yes. So BRX is BR times the cosine of theta, and BRY is BR times sine of theta. So here BRX, the X component of the radial component of the flux density in air gap, is what is the peak value of the fundamental harmonic? Let's consider it 1, not is important here. So simply I write cosine of theta, cosine of t times point times cosine of t. Here I should write the B1 peak value. I considered it equal to 1. Yes. So if you want to consider the real number, yes, you can use that. So here, what is the BR? The Y component is sine. So BRX and BRY. Let's run the code. Here we have these flux density vectors generated by the phase A. Let's use the blue color for the phase A and change the thickness of the line to 1.5. Okay, now this is a better visualization. This is the field generated by the phase A. What about the phase B? For the phase B, as you know, we have 120 degrees phase shift. We have the same function, just we should consider 120 degrees phase shift. So here, this is for the phase A actually. I want to have these quiver functions. This is for the phase A, and the quiver function for the phase B is this one. Let's add it. This is for the phase A. For the phase B, the quiver plot BRX, we need to consider 2 times pi divided by 3 for a 2-pole motor. Yes, we have 120 degrees phase shift. So when the magnetic axis of the phase A is here, the magnetic axis of the phase B is here. So let's run. We have these two fields peak values, right? When we have rated currents in the coils. So here let's use this color red and reduce the thickness of the lines. The phase B, and finally we can plot the phase C. So here for the phase C we have 4 times pi divided by 3. Use this color. This is for the phase C. Yes. So I generated these graphs when I have peak currents in the coils. But you know that this B1 is actually the peak value is equal to the current of the phase A. For example, this is BRA. This is the current of phase A times a constant, right? I write K1 here. So in the case of considering linear permeabilities assumptions that we have, you know that in general the field generated by the phase A in the air gap is a nonlinear function of the current. But we consider that we assume the simplifications and we can extract the current from this expression. Yes, so I can write B R generated by the phase A as a function of theta is the current of the phase A times the constant K1 times cosine of theta. You know that. So I want to use these variables and use time functions. We know that for a three-phase induction motor during the steady state operation, the value of the currents are not equal. Yes, at any instance of the time. We know that if we use a star connection, the summation of the currents are zero. And in ideal case, also when we use the delta connection for a well-designed motor, yes, we want to have the same equation. I mean, IA plus IB plus IC to be equal to zero. So let's consider the star connection. Okay. So here, if I assume these time functions IA, IB, IC, I can modify these plots. So if I have these time functions, this is the time actually. I want to change the time from 0 to what is the frequency of the supply? In this case, the frequency of the supply, let's consider equal to 50 hertz. This is the supply frequency. The time period is 1 divided by Fs. And I want to consider two electric periods. Yes, 2 times Ts. The step size Ts divided by, let's consider 30. So I want to consider this value for the current of the phase A that is equal to, excuse me, here this is the number of points that we consider between 0 and 2 times Ts. If I consider this time a step, actually I should divide the full period, that is this one, divided by this point. But let's consider number of time points equal to 60 and simply use it here. So this is the number of time points. And this is the electrical period of the currents. The current of the phase A, let's consider peak value equal to 1 amps and consider this function cosine of omega E or synchronous electrical frequency times time. What is the synchronous angular electrical frequency? Omega S is 2 times pi times Fs. So this is the synchronous angular electrical frequency. Yes, the unit is radian per second. So consider this function, this value for the current of the phase A. And if we have this current for the phase B and this for the phase C, the same function, 2 pi divided by 3 and here minus 4. So if I generate a new figure, just I want to visualize the value of the currents. Plot time and IA, the current of the phase A, B, and C. So, as you can see, here is the current of the phase A, phase B, and phase C. So, yes, when we have three phases, this is the phase A, and this is the phase B, this is the phase C. So when we have peak value here first, and then we have peak value for the current here, and then here we should have this rotating field. So I can modify these graphs. Here is the quiver plot of the phase A. Let's run this code again because I deleted the graph. This is the quiver plot of the phase A. I can modify the U data and V data. These are components of the flux density vectors. So here, how we can visualize the rotating field for I equal to 1 to the number of time steps, quiver plot of the phase A. This is equal to quiver plot dot U data is equal to, actually we need to do the same calculations here. We have to modify the amplitude of the flux density vectors generated by each phase using the currents. So here, this is the BRX and BRY for the phase A. I should modify it by the current at the time step I. Yes, so modify the amplitudes, and this is BRX. Modify the V data is BRY. So here, let me delete this figure. Okay, and let's hide these two plots. Just I want to visualize the phase A. Here, when we update the graph, we should write this function draw now to update the graph, the figure, and let's pause 0.1 second to check all frames. So let's run the code. As you can see here, we have a pulsating field, but why we cannot visualize it good? Because when we use the quiver function, we should off the scaling. So when the scaling is on, we cannot visualize the variations good, because MATLAB auto scale flux density vectors. So here I off the flux density amplitudes scaling and set the color equal to blue. So let's run the code again. Here you can visualize the variation of the field generated by the phase A. Yes, we have a pulsating field. Okay, so let me check. We don't have this. This was for the phase B, excuse me. This is for the phase A. The magnetic axis is here. Yes, we have a pulsating field generated by the phase A. So let's increase the number of electric periods to 5, and this one equal to 150. So we can visualize this animation better when we have a sinusoidal current and we excite the phase A using this sinusoidal current. We have this pulsating field that is generated by the phase A. So what about the phase B and phase C? Yes, this is the phase B and phase C. Let me copy this of scaling, and we can do the same calculations for the phase B and C. This is IB and IC minus 2 times pi divided by 3. For the phase C is 4. So this is B and this is C. Okay. So we have these currents, these quiver plots. We have these currents 120 degrees phase shift between them. So if I run this code, as you can see, we have 3 pulsating fields. But these 3 pulsating fields generate a rotating field when we consider the net value. Yes. So here we visualized the fields generated by these 3 phases. But you know that we can write the air gap field generated by the stator winding is the B generated by the phase A plus the B generated by the phase B plus B generated by the phase C. How we can visualize this? I can use this method. I want to visualize these two animations on the same figure. So let's use this subplot subplot 211, okay, to generate these graphs, the laminations, and subplot again 212, then make this subplot active to plot these quiver functions, and then I make this subplot active to plot the summations of these 3 functions. So this is the BRX generated by the phase A, B, and C. This is the Q, the net value for the air gap. This plot for the gap. We can use this method. Actually, we can pick up the U data of the phase A. This is the BRX, the net value for the gap is this one plus quiver function B dot U data plus the quiver function C U data. The Y component, let's use the same. The Y component is the V data. Okay. So if I plot here, only I generated this graph for one instance of the time. Here you can see these 2 figures. Yes, I want to generate the field for all times. So how I can do that? Let me use 1 2 instead of 2 1. So 1 2 1 2. This is better. So at each instance of the time, we can update also this quiver plot. Yes, that's all. So if I run this M file, as you can see, we have these figures. Excuse me, here I don't update the figure. I should update the figure like this for the gap. I replot again and again. That is not correct. So now this is correct. We have 3 pulsating fields, and in total, if we sum up these 3 fields in air gap, we have this rotating field. The amplitude of the rotating field is constant. Yes. Okay, so in the next parts, when we develop the two-axis model of the motor, I will derive the detailed expression for the rotating field. Okay, so how we propose a two-axis model and how we can develop a two-axis model for induction motors. In this M file, in this example, I try to visualize this rotating field. So you can visualize this rotating field using the plots instead of the quiver functions. That is also interesting. You can do it yourself as a practice. So I think it's enough for this video, and let's continue development of the abstract model in the next video.